My name is Nguyen. I am a PhD candidate at Nanyang Technological University in Singapore. My supervisor is Professor Nguyen from Nanyang Technological University. My co-supervisor is Professor Douglas L. Jones from University of Illinois at Urbana-Champaign. My research topic is sound event localization and detection. I would like to thank DCASE organizer and DCASE community for making impactful progresses in audio research by providing curated dataset and steering the research directions. Today, I'm going to present our paper, Ensemble of Sequence Matching Networks for Dynamic Sound Event Localization, Detection, and Tracking. The task of sound event localization and detection is to classify the sound sources and estimate the directions where the sound comes from. Sound event localization and detection, short form SELD, that uses small arrays consists of two subtasks, which are sound event detection SED and direction of arrival estimation or DOA estimation. These two subtasks are mature resource topics. However, joining these two subtasks are not trivial. SED and DOA estimation require different information from the audio input signals. SED mainly relies on time frequency patterns, while DOA estimation mainly relies on the phase or magnitude differences between microphones. However, SED can potentially improve the performance of DOA estimation by providing accurate acoustic signal detection. Likewise, DOA estimation can potentially improve the performance of SED by spatial filtering to reduce the interferences in multiple source conditions. To solve sound event localization and detection problem, Adavan et al. Proposed a single input, multiple output convolutional recurrent neural network (CRNN) called SELDNet that jointly optimize SED and DOA estimation. However, the joint optimization reduced the performance of each task. To mitigate this problem, Cao et al. Proposed a two-stage strategy to train two almost identical CRNN models for two tasks separately. The SED outputs are used as masks to select the corresponding DOA outputs. This two-stage strategy significantly improved the SELD performance. Our previous research tackled the SELD problem differently. We solved SED and DOA estimation separately. After that, we trained a recurrent neural network to align the SED and DOA output sequences. The proposed sequence matching network also includes a convolutional network to learn the pattern from the raw DOA histograms. The experimental results show that this sequence matching network outperforms both the jointly trained SELD model and the two-stage approach. The sequence matching network works well for static sources. However, it is not directly applicable for dynamic sound sources. The reason is that dynamic sources require much higher angle resolution than static sources. Therefore, the angular dimension of the DOA output sequences is getting prohibitively large. Even if we use an angle resolution of 5 degrees, the angular dimension is 1296, which is quite large to train the model effectively. Therefore, we propose to use 1D histograms for azimuth and elevation separately as input features to the sequence matching network instead of the joint 2D histogram. This is the DOA estimation algorithm used in our research. We use a single source histogram analysis method to estimate the directions of arrival of multiple sound sources. The algorithm selects time frequency bins that are above a noise floor and contain energy mostly from one source to mitigate the problem of noise, reverberation, and multi-source. For each selected time frequency bin, a DOA is estimated and populated into a 2D histogram for each time frame. This histogram is then vectorized and stacked along time dimension to form the DOA output sequence. In this new research, we propose to use 1D histogram as an input sequence to the SMN instead. So, for each selected time frequency bin, a DOA is estimated and populated into two separated histograms, one for azimuth and one for elevation. These histograms are stacked along the time dimension to form the DOA output sequences. SED network that you in our system is borrowed from the SED network of the two-stage paper by Cao et al. Input features to the network are log-mel. Our experimental results show that spatial features do not have sound event detection for dynamic sources. We use a combination of several data augmentation techniques to further improve the SED performance. We use the 2020 spatial sound events dataset with ambisonic format to evaluate our proposed approach. The dataset consists of 600 recordings for development and 200 recordings for evaluation. Our results are reported on the test set of the development dataset. The dataset consists of 14 sound classes, and we set an angle resolution of 5 degrees for our DOA estimation algorithm. There are two evaluation metrics available for SELD tasks. The 2019 matrix evaluates SED and DOA separately, while the 2020 matrix takes into account the association of the sound classes and their directions. We use the 2019 matrix to evaluate our individual subtasks and use the 2020 matrix to evaluate the final task. We compare our approach with a baseline algorithm and our previous solution. The baseline is a jointly trained SELD model that are provided in the 2020 SELD challenge. The SED net is the SED network of the two-step method with additional data augmentation and different input feature. The DOA hist is the histogram algorithm for the DOA estimation. Both the SED net and the DOA hist produce the input sequences to our proposed sequence matching networks. Our previous SMN solution is called SMN2D because it used 2D histogram as input. As a result, the applicable DOA resolution for this network is 10 degrees. Our new proposed SMN solution is called SMN1D. It uses 1D histograms of azimuth and elevation as input. We use a DOA resolution of 5 degrees. We have experimented with a DOA resolution of 2 degrees, but it doesn't improve the final performance. The experimental results are shown on the screen. We can see that both the SMN model outperform the baseline model by a large margin. The proposed SMN1D significantly improved the DOA error compared to the SMN2D. One obvious reason is because the SMN2D only used lower DOA resolution. Other measures for the two SMN models are almost the same. The SMN models has higher DOA error but higher frame recall compared to the standalone DOA estimator. To further improve the performance, we do Ensemble for SED models. We train 4 different SED models and combine the outputs by taking their geometric mean. The Ensemble significantly improved the SED performance. We pass this SED Ensemble to the SMN with 1D histograms. We call this new SMN1D Ensemble. The SMN that takes SED Ensemble as input outperforms the normal SMN. The overall SED error reduced from 0.401 to 0.381, while the DOA error reduced from 15 degrees to 13.5 degrees. We can see that SED performance have a very heavy weight in the final SELD task. To further improve the SELD performance, to participate in this year's DCASE challenge, we train multiple SMN models with different input lengths of 4, 6, 8, 10, and 15 seconds. This example of multi-length further reduced the SED error from 0.381 to 0.359, improved the SED F1 score from 0.694 to 0.712, reduced DOA error from 13.5 degrees to 12.1 degrees, and increased DOA frame rate from 0.815 to 0.820. We retrain all our models using the best setting and all of the development data. Our proposed solution ranks second in the team ranking of this year's SELD challenge for dynamic sound sources. Our evaluation results are better than our test results because we use a larger training set for evaluation. In conclusion, the sequence matching networks work both for static and dynamic sources. Separated azimuth and elevation inputs work better for high-resolution DOA estimation. The sequence matching networks outperform jointly trained baseline for SELD, and ensemble of multi-scale sequence matching networks significantly improve the SELD performance. Thank you very much for listening, and I hope to see you in the live Q&A session.